Okay, so next is exercise 14. So this one is a starred exercise, which means that its solution is supposed to be somewhat difficult than the other exercises. Anyway, so let us see what we can do. Okay, by the way, what the exercise asks us is this: we are given an infinite set S, and it is given that S can be brought into a one-to-one correspondence with the set of integers. That means there is a one-to-one correspondence between S and the set of integers. Then we have to prove that there is a one-to-one correspondence between S and the Cartesian product of S with itself. Okay, so let us start the solution like this. Since there is a one-to-one correspondence between S and the set of integers, which of course we are denoting by this symbol. Okay, blackboard bold Z. There is a one-to-one correspondence, say sigma, from the set of natural numbers onto S. Why? Because you see, we already know that the set of integers has a one-to-one correspondence with the set of natural numbers, and using that fact and this fact that there is a one-to-one correspondence between S and Z, you can set up a one-to-one correspondence between the set of natural numbers and S. So here's something is written. See the solution to exercise 10. Exercise 10 means the exercise 10th exercise here in this list of exercises. There, whatever I have said just now, something along the lines of that is given there in this solution. So basically here we just are using the fact that there is a bijective mapping between S and Z, and there is one between Z and N. So using these two things, we can set up a bijective mapping between N and S. Okay. Now, using this sigma, we can set up a natural one-to-one correspondence say tau from N cross N to S cross S. Given by, okay, now we say natural because the definition of this function tau, you will see that it naturally uses sigma. How? You take an element from here, it will be an ordered pair of integers. Its tau image is defined to be equal to m sigma comma n sigma. So you see that once we choose such an ordered pair, m and n are integers, natural numbers. So on them we can apply sigma, and the images will be again in S. So this is an ordered pair where the coordinates or the elements or the components of the ordered pair are coming from S. So it's an element in S cross S. And moreover, since this has been defined in terms of sigma, which is a well-defined map, so tau is also well-defined clearly. So that's what we write clearly. Tau is well-defined. In the original solution that I have written, I have not shown that this tau is a one-to-one correspondence, but here for the sake of understanding we will just go through the details and see. It's very easy to show that tau is a one-to-one correspondence. Now let us first show that tau is one-to-one. Let us take two elements in its domain such that their tau images are equal. We will then have to prove that the elements are equal. Such that m1 comma n1 tau is equal to m2 comma n2 tau. Then m1 comma n1 tau is m1 sigma comma n1 sigma, like that. This one is m2 sigma comma n2 sigma, which implies m1 sigma is equal to m2 sigma and n1 sigma is equal to n2 sigma. But now sigma is a one-to-one correspondence, so it's a one-to-one mapping. Since sigma is one-to-one, the last two equations give us m1 is equal to m2 and n1 is equal to n2, and that implies m1 comma n1 is equal to m2 comma n2. So we started off by assuming that the images are equal. Now we have proved that the elements are also equal. That tells us that tau is one-to-one. So, or hence, tau is one-to-one. Next we show that tau is onto. Next, this is also as easy. In fact, it's more easier than showing that tau is one-to-one. Next, let S1 comma S2 be an ordered pair in S cross S. Okay. Then S1 and S2 are both elements of S. Now sigma is a mapping from n into s, from the natural numbers into s, which is being a one-to-one correspondence, sigma is onto. So we are going to use the ontoness of sigma now. Since sigma is onto, there exist say A and B belonging to the set of natural numbers such that S1 is A sigma and S2 is B sigma. Then S1 comma S2 is A sigma comma B sigma. But since A and B are natural numbers, so by the definition of tau, this is nothing but the tau image of the ordered pair A comma B. So every element in S cross S is the image of something in n cross n under tau. Hence tau is onto. So we have shown that tau is actually a one-to-one correspondence, right? Now we are going to use one result from Terence-Tau's analysis 1, and that result is this. Now by corollary 8.1.14, tau. By now you know what this means. We know that there is a one-to-one correspondence say I call it eta from n to n cross n. And what is the statement of the corollary? The corollary says this: 8.1.14 says just this. If x and y are sets, are countable sets. Since we are not stating this corollary in the context of something, I mean when we will actually prove this corollary in Tau's analysis, we will be doing it in a context, right? For example, in the context of countable sets. So there we will automatically know from other usage of these symbols x and y that they are sets. But since now we are mentioning it within a solution, so let us just say that they are sets. Otherwise, although I am not sure that this countable, this adjective is used anywhere else in mathematics to something other than a set, and I am not aware of that if there is something like that. So to avoid any confusion, let us say sets. The actual statement does not say sets specifically. If x and y are countable sets, then so is their Cartesian product. Then x cross y is countable. So we know that the set of natural numbers is trivially itself a countable set. I mean, those of us who know about countable sets. So according to this lemma, if you take x and y both to be the set of natural numbers, then this becomes countable, and the definition of countability just says that there is a one-to-one correspondence between the set and the set of natural numbers. So that's how we are getting this one-to-one correspondence. Okay, so now we can use these three things because we have sigma, we have tau, and we have this eta. Hence, okay, so we had to set up a one-to-one correspondence between S and S cross S. Okay. So sigma is taking me from, let us just see here roughly, sigma takes me from N to S, tau takes me from N to N cross N, not N to N cross N, sorry, tau takes me from N cross N to S cross S, and eta takes me from N to N cross N. Okay, so what we do, we take the inverse of sigma. So then we will start from S and we will come to N. Sigma inverse will take us from S to N. Then from there, eta will take us from N to N cross N, and finally tau will take us from N cross N to S cross S. Hence, sigma inverse composition eta composition tau from S to S cross S is a one-to-one correspondence. And there the solution ends. Okay, after this we have 15. Only 2 more exercises are left, 15 and 16. The solution that we have just seen now of 14, it looks somewhat easy, but you have to understand that we have used some things which we have not proved here. So proving those corollaries or the theorems from which the corollary is coming, that is the hard part of this problem. Since the exercise says nothing about the theorems that we will need after all, in fact we are using the concept of countability. So that's why figuring it out on your own is quite difficult. I mean, you have to come up with, you have to think originally of countability without ever looking at some source to know that that's how you have to proceed to get the solution. So that constitutes the difficulty of solving this exercise. So that's why a star. And this one also has a star, although I'm not sure why this one has a star, because its solution is not as difficult as this one. Anyway, given 2 sets S and T, we declare S less than T. This is just a symbol, okay, we are defining something. Usually we never write a set is less than another set and use the ordinary less than relation that we have between two numbers, but here we are defining it like this, or you may also call it S is smaller than T when, what is the condition? If there is a mapping of T onto S, but no mapping of S onto S. S onto T. To understand this definition, we can take one example. Say this is my S and this is my T, which have totally different elements. In fact, they are disjoint, there is nothing common. Now you can see that in the usual sense of number of elements, S is smaller than T. S has 2 elements and T has 3 elements. However, this definition does not say anything about number of elements. It is defined in terms of mappings. Note one more thing, that although we can understand this, why we say S is smaller than T in this situation, by this simple example which involves finite sets, but the actual definition also works for infinite sets. Okay, so here what the definition says is that we can find there is one onto mapping from T to S, which we can find. Actually we can find many onto mappings. One of them is this one. Okay, and you can see that because S is smaller in the usual sense than T, so any mapping would not be, no mapping would be one-to-one. However, we are not bothered about one-to-oneness here. We have defined it in terms of onto function. So the point here is that there is at least one onto function from T to S, but no matter how hard you try, you can never find an onto function from S to T. You can map 1 onto 3, 2 onto 5, but then 4 is left out. If you want to define a relation like this, that is okay, but that is not a mapping. Okay, so that's why according to this definition also, S is smaller than T. But this definition takes care of even those cases where S is infinite, T is also infinite. Now under this definition, the exercise then asks us something. Oh, we have to prove that this relation between two sets is transitive. Prove that if S is smaller than T and T is smaller than U, then S is smaller than U. Okay. So let us see the solution. Since S is smaller than T and T is smaller than U, there exist onto mappings. Onto mappings sigma from T to S, and this is S, and tau from U to T. But at the same time there is no onto mapping from S to T and no onto mapping from T to U. So we mentioned that one also. And there is no onto mapping say sigma prime from S to T and there is no onto mapping tau prime from T to U. Now using this information we have to prove that S is smaller than U. Okay. Note that the composition tau composition sigma takes us first from U to T and then from T to S. So it will ultimately take us from U to S is onto. This is I think by exercise 8, although here I have not mentioned. It is just that result which says that the composition of two onto functions or onto mappings is again an onto mapping. So we have used that here. Now we have to show, okay, so one part is over. We have produced an onto mapping from U to S, but now we have to prove that there is no onto mapping from S to U. This we will prove by contradiction. So we are going to suppose that there is one such mapping and then try to arrive at a contradiction. Now suppose there exists an onto mapping what shall I call it? Let me call it eta again, from S to U. One such mapping exists, that is our supposition. Okay. Now eta takes me from S to U and tau takes me from U to T. Note that this is already onto two onto mappings, and according to our supposition this is also onto. Then eta composition tau, it takes us from S to T, is an onto mapping because both eta and tau are onto. Eta is onto by our supposition, tau is onto, that is the hypothesis, it's given. But this contradicts this contradicts the thing with which we started, what is given to us, that there is no onto mapping from S to T, but here we have found an onto mapping from S to T. This contradicts the hypothesis that there is no onto mapping sigma prime from S to T. So our supposition is wrong. That is the only conclusion, because other than this supposition, whatever we have done is logically correct. So, but still we have got a wrong result or something that contradicts the very premise of this problem. So that means the only place where we have made a mistake is in the supposition, blind supposition. Our supposition is wrong. That is, there is no mapping of S onto U. And now we are through, because we have produced an onto mapping from U to S, and we have also proved there is no such mapping from S to U. So S now has to be smaller than U by definition. Hence, S is smaller than U. So here the solution ends. And now the final problem. I think it's better if I refill. We can write the statement here itself. Exercise 16. This one, however, is not starred. See, the way and the ease with which we solved this problem, that makes me suspicious that the solution is correct. It is too easy to have a star. I mean, the problem, the solution, you can see how easily we have got the solution. I don't understand why Herstein has put a star on it. You go through the solution carefully and let me know if at all there is some mistake. I have seen many times, I have not found any mistake. So let us see the 16th one now. This one is also similar. It involves the same concept of a set being smaller than another set. However, now we have come to finite sets. If S and T are finite sets, having M and N elements, respectively, prove that if M is less than N, then S is less than T. So this shows that the definition of one set being smaller than the other that we have seen in the previous exercise, that involves mappings, actually matches with our usual idea of a set being smaller than another set if they are finite. The example that we have discussed, after stating that problem, the previous one, that will now be substantiated. That is, whatever we think normally when we have two sets, which one is smaller, matches with whatever we have defined in the previous exercise. So here we are given two finite sets. S has m elements, T has n elements.